In this segment, we'll continue our discussion of strings and pointers, looking at the stir-copy function, and doing some important review on why assignment statements aren't actually statements at all. Let's take a look at stir-copy on line 4 of the sample code. As I said earlier, this is a handcrafted version of the stir-copy function from the C string libraries, and it works the same as stir-copy. Note, first of all, that it takes two character pointers, consistent with the idea that strings are just character pointers. Stir-copy expects the source to point to a null-terminated sequence of characters, and target to point to enough space into which to copy those characters, including the null. Guaranteeing this is the job of the caller. If you copy a too large string into a too small space, a too large source into a too small target, stir-copy and the library stir-copy will cheerfully overwrite the end of the target space with the usual consequence. So then, how does this code work? Seems like that little while loop is doing an awful lot in one header line. I'm going to ask you to tell me how it works in some questions shortly, but first, a bit of C review from prior study is in order here. Recall our earlier lecture discussions about expressions such as star source plus plus, including the relative precedence of the operators. Plus plus will get done first, star second. And then recall from prior C work that assignment statements are actually expressions having a value. So if we write a equals 42 like that, this not only copies the 42 into A, but the entire assignment also has a value. The value is simply whatever was assigned, 42. This means, however, that we may use A equals 42 as part of a larger expression, e.g. C equals 4 plus A equals 42. Well, that copies 4 plus 42, or 46, into C. Or array bracket A equals 42 equals 0. That indexes array by 42. Or even taking the square root of A equals 42. Importantly, the assignment into A takes place in all of those cases. The value of the assignment is an additional feature, and it allows more concise code, which is a big virtue in the C mindset. Our earlier look at pre- and post-increment and decrement operators ties into this. Those are also assignments of a kind, and they have a value. There's a related concept to review here, too. If assignments are expressions, then why can we use them as a statement, ignoring their value? Because C allows expressions as statements, and simply drops the expression's value on the floor if you don't use it. You've been taking advantage of this since your first Hello World program, in fact. Printf is a function, and it returns an integer, so a statement like printf Hello World is an expression, in fact. But when you use it as a statement, the integer return value of printf is simply dropped. Printf's return value, by the way, indicates how many of the format specifiers were successfully printed. It's supposed to allow error checking of printf calls, but no one ever bothers with it. This expressions are statements rule means you're always welcome to ignore the return value of a function and just use the function call as a statement. So let's see. Does that mean you could write, say, 2 plus 3 as a statement? Like that? Yep. The machine, in effect, says, wow, 5, and then forgets it and moves on. In fact, a good optimizing compiler may just drop the line entirely since it has no effect. This sort of thing is not useful, of course, except as the source of an occasional entertaining bug. Like a number of popular C features, the assignments are expressions and expressions can be statements rule persists in dozens of languages. Java, JavaScript, C#, C++, all of whom originally drew it from C. And to close this review, let's talk about what is perhaps the most famous of C bugs, the single equal sign error. Every C beginner, and sometimes even a C professional, accidentally writes what we have up here, if A equals 1, when they meant to write, of course, if A equal 1. The maddening thing about this bug is that it compiles and runs, but it doesn't do what you'd expect. To understand it, you really also have to assume that A is an int, which is almost always the case for these, and you must recall that C uses int values to represent true or false, non-zero values being true and 0 being false. C has no true Boolean variables. All comparisons and Boolean operations like AND and OR are done with ints. We won't review that here. It's expected prior background, and you should look it up if needed. So question 1. Given that assignments are expressions and ints are Booleans, why does if A equals 1 compile? And what does it do exactly? Coming back from a pause, answer 1. It compiles because you can put an integer expression into an if test. And A equals 1 is an integer expression with the value 1. The value 1 also makes the test automatically true, regardless of the original value of A. This particular example even has the interesting property of setting A to 1, in effect forcing the intended A equals 1 test to be true. The baffled programmer sometimes reaches the following situation where they can't figure out why the thing is still running, so they'll be printing the value of A in here, and then above it setting A equals 0, and confirming that in fact it's not 1, and then they print it and the if statement runs and it turns out to be 1 after all, and finally realize that the problem all along was that they've been making it be 1, not testing it to see if it was 1. So let's also follow this up with a question 2 here. C allows what some people call chained assignments. We can write something like A equals B equals C equals D equals say 0, like that. That would assign 0 into all 4 of those variables at once. This is not an added feature of the language. It follows naturally from what we've just discussed. So how does it do that? And give an answer by redundantly parenthesizing the chained assignment here in a way that shows what's really happening. Coming back from a pause, you should have parenthesized it like this. What's going on is that it's an ordinary D equals 0 assignment there, and because assignments are done in right to left order, it's done first. And it has the value 0, which then becomes the right-hand side of a ordinary C equals 0 assignment, which also has the value 0, of course, and becomes the right-hand side of an ordinary B equals 0 assignment, and that in turn for the A. So the chained assignment feature is really not a special feature. It's just a way of using the fact that assignments have a value. Okay, with all that review, let's take a look now at line 5 in stir copy and see what's going on. Assume that target and source point respectively to string 1 and string 2, and that those contain professor and project as shown in the diagram. So we'll break this into 2 questions. Show what happens on the first while loop iteration, including any changes to the strings and the 2 pointer parameters. On this first iteration, is the loop test true or false? Notice that the test is an assignment, not an equality check. So, coming back from a pause there, as the change diagram shows, the increments advance both pointers to the second characters in their respective strings, to the R's in our case here. But since those are post increments, the addresses that get dereferenced are actually those of the first characters. So the first P is copied from string 2 to string 1. And this is redundant in this example, but wouldn't be if the strings had different first characters. And the value of the assignment is the ASCII code of the assigned character P, which is non-zero. So the loop test is true. And the loop is ready for the next iteration, with the pointers already advanced to the second characters. So the loop continues, walking down the source and target strings, copying 1 character at a time across, with the test being true as it copies each character. And question 4. When does the loop stop? And what is the last character to be assigned across? Coming back from a pause there, it stops when source points to the terminating null in the source string. This gets copied across to the target string, and the value of this assignment is 0, or false, ending the loop. By the way, I changed the target string to show what had been copied in the prior iterations. This is an example of why null, or ASCII 0, was a good choice for marking the end of a string. The while loop can be so concise, in part because the only assignment that produces a false value is that of the terminating character. And note, by the way, the lingering R and 0 at the end of professor here is moot. It'll never be reached by any string function, since they all stop at the first null here. And then finally, question 5. What happens if we pass strcpy a source string that has no null at the end? Stop and think about that. Well, answer 5, after a pause here, is a lot of characters get copied, since strcpy will just keep going until it sees a null, charging through memory, copying all of the characters, quote-unquote, it sees over to the target. Eventually, some byte in memory will be a 0, and the loop will stop. Indeed, it's not uncommon for a 0 byte to be hit by accident very quickly, since many bytes in the overall memory are zeros. But this just means that such a bug might actually go by without damage, making it yet another unlucky C bug. And finally, we come to our typical outside research question here. So look at materials other than from the lecture to answer this. Question number 6, is there a way to call strcpy, or some version of strcpy, that will ensure that the loop stops after some number of characters, presumably the limit of the target string size, even if the source string is too long, or lacks a null character altogether? After a bit of pause and several minutes worth of research, I would expect, the answer is unless you already knew the answer is strncopy. This takes a third integer parameter, giving the max number of characters to copy, and it's often considered good style to use it for the sake of protecting against security problems resulting from malicious user strings.